Welcome to Chemistry with Mr. Brazil. Today I will be discussing ideal gas law, Dalton's law of partial pressures, and a little bit of Graham's law. Let's start with gas law, ideal gas law. First of all, ideal gas law is an equation that looks at gases as if they're infinitely small particles that when they collide, energy isn't, transferred. It's an equation that works very well at low temperatures that we tend to deal with. So in this equation, you're going to see V is equal to volume, but N, that's the number of moles. So this equation, you take the combined gas laws, and now you account for the number of particles, not changing per se, right? What's interesting is they're both equal to each other, so that means they're equal to a constant, which is called R. This constant for high school will tend to be 8.31 liters kilopascals mole Kelvin. And I tend to put K before mole because we never kill a mole, but mole Kelvin. So it has 4 units. Now, for those who are going to go on to college, you may see this, and there may be other high school teachers who use the 0.082057 liters atmosphere mole Kelvin. And even in physics, they will have units with joules in it. This does have energy. But for my students, we tend to use the 8.31, real simple to remember, liter kilopascal in the numerator, and the denominator mole Kelvin. Okay. Let's see how we're going to use this. I have a sample problem. First of all, the equation is always written as PV equals nRT. Pivnert is kind of the common words or slang that chemists like to use. So here's an example. A deep underground cavern has 2.24 times 10 to the 6 liters of methane gas at a pressure of 1.5 times 10 to the 3rd kilopascal, and the temperature at 42 degrees Celsius. Notice that in the units that had Kelvin, yes, with gas laws, always convert temperature to Kelvin. Now we want to determine how many kilograms of methane are in this cavern. Well, here's the cool thing. We can solve for the number of moles. Now, you can list your variables and make the necessary conversions. Sometimes folks will make pressure into ATMs, and you need to convert to kilopascals. So 1 ATM is equal to 101.3 kilopascal. R is 8.31 liter kilopascal mole Kelvin. And convert our temperature always to Kelvin. So you can do a list, you can label, but you will always write your equation as you know it, PV equals nRT, then solve for the variable that a question is asking for. In this case, it's asking for kilograms, but we know how to convert from moles to kilograms using molar mass later. So in other words, rearrange your equation, okay, to PV over nRT. If a variable is on top on one side of the equal sign, it will be on the bottom on the other side, okay? So I'm going to go to the next slide. Now we plug in our variables or our knowns. 1.5 times 10 to the 3rd kilopascals, the 2.24 times 10 to the 6 liters. And notice how I did R. I wrote R as liter kilopascal mole Kelvin, kept it like this, and I took the converted temperature to the 315 Kelvin. And now I can start removing my units, canceling to make sure I'm okay. Kelvins will cancel. The mole here is going to reciprocal up. And that means we now have our answer in terms of moles, 1.28 times 10 to the 6 moles methane. Well, let's convert this to mass. What we can do is we take the moles, whatever unit's on top, put it on the bottom. So parenthesis, fraction bar, moles, CH4, methane. The molar mass, 12 plus 4, is 16 grams. And since the question wanted it in kilograms, 1,000 grams divides into 1 kilogram. And our answer will be 2.05 times 10 to the 4 kilograms methane. So the ideal gas equation is a very powerful tool for finding moles, and we could determine molar mass of a gas. Okay, so let's go on to some important topics. So there is a departure. Ideal gases assume that these gas particles are itty bitty small, super small, and they're not interacting. The reality is molecules, gas particles do attract and repel. They also have volume. So a real gas acts like a matter. And so at high temperatures, the ideal gas law equation fails. So at very high temperatures, it doesn't work. But at room temperatures and lower, it works fine, and it does model what gases will do. So it's a pretty powerful tool. Next. So Avogadro's hypothesis, equal gases of at the same temperature and pressure contain the same number of particles. Here's what that means. You have a big gas particle and a small gas particle, but they're in the same volume. You're going to have the same number of particles. So for example, I have methane here, which is made up of 5 particles, okay? And helium gas, well, they're in the same volume and the same temperature. You're going to have the same number of particles, okay? So, let's bring this back again. In other words, methane is made of 5 particles, 1 carbon and 4 hydrogens, okay, individually. But since it's a molecule, it's 1 particle, and there are 5 of them in this container. Here, there are just 5 helium atoms, okay? But at the same temp, same pressure, you're going to have the same number of particles in that container, for this container having the same volume. So that's what this all means. What's cool about it is at STP, a condition that's only for gases, 1 atm or 101.3 kPa or 760 millimeter mercury, same pressure, but at 0 degrees Celsius or 273 Kelvin, you get this, 22.4 liters per mole, and for gases only. This is not for solids, for liquids. Well, there's Dalton's Law of partial pressures. This is a pretty cool concept and an important one. If you have a container and it has different number of moles, which we're not going to take into account for high school, but for a different number of gases, different gases at different pressures, their total pressure for that container is the sum of those gases. In other words, you got a mixture of gases at different pressures. For example, this container with different gases, oxygen, water, nitrogen, fluorine, carbon dioxide, that total pressure is equal to the contribution of each gas pressure. So there's a general equation for you. So I have an example on the next slide. So we have a gas mixture containing oxygen, nitrogen, and carbon dioxide, and its total pressure is 0.787 atm. What is the pressure of oxygen in atm? So we want the answer in atm, and we got if the pressure of carbon dioxide is 45.6 millimeter mercury and nitrogen is 24.8 kilopascal. Okay, and usually my questions are worth 3 points. So first, write your equation as you know it. Next, rearrange and solve for oxygen. So if this is plus on the right side of the equation, it's going to be minus. So for each one. Next, plug in your values. We need to convert the 24.8 kilopascal to atm. So 1 atm equals 101.3 kPa, while 45.6 millimeter mercury, its conversion is 1 atm is equal to 760 millimeter mercury. So those units will cancel. So always follow the mantra. Whatever unit's on top, put it on the bottom, and you'll know which conversion to use. Okay? The answer for this is simply 0.48 atm. There you go. And it's not too tough, but it does take a little bit of practice, okay? Next, this is Graham's law and mainly vocab. Diffusion. This is the tendency of gas molecules or particles to move toward an area of lower concentration. So you got a candle burning in a room. you don't, or down the hallway, you don't smell it when it first starts, but as the gas starts to increase, it starts to diffuse out through the hallway, and you start smelling a little bit of an odor. As you get closer to the candle, you will smell it more so. So gas particles like to just spread out. Next is effusion. So this is an interesting one. You got an enclosed container, and you poke a tiny hole. And if you have a mixture of gases, the smaller particles, the smaller gas molecules or smaller particles will come out faster than the larger ones. And so this is just a general understanding. There's actually an equation to figure out the velocity of these particles. So, but that will be for another time, and we'll save that for later. Study ideal gas law, read it, watch other videos. It's pretty straightforward, okay? Keep practicing and enjoy your chemistry. Bye.